Eulerian graphs, an important concept in graph theory that originated from a very famous real-world problem, the Königsberg Bridges Problem. Eulerian graphs help us understand how we can traverse every edge of a graph exactly once, and they form the foundation of many routing and network applications. This problem comes from the old city of Königsberg, which had 7 bridges connecting different land areas. The question was simple. Is it possible to walk through the city and cross each bridge exactly once? Euler solved this by transforming the land areas into vertices and the bridges into edges. The problem turned into checking whether the corresponding graph contains an Eulerian trail, meaning a path that uses every edge exactly. Now let's define what Eulerian graphs are. A connected graph is Eulerian if it contains a closed trail, a path that starts and ends at the same vertex, and this trail uses every edge exactly once. If the graph has a trail that uses every edge exactly once but does not end where it started, then the graph is called semi-Eulerian. So the key difference is whether the trail is closed or open. Euler provided a simple and powerful condition for determining whether a graph is Eulerian. He stated that a connected graph is Eulerian if and only if every vertex has an even degree. In the slide you can see examples. The first and third graphs are Eulerian while the middle one is not. The key reason is that the Eulerian graphs have all even degree vertices. Euler's findings relate closely to this lemma. If every vertex of a graph has degree at least 2, then the graph must contain a cycle. A cycle is crucial for Eulerian trails because an Eulerian graph is basically built from cycles that join together. This leads to 2 important corollaries. First, a connected graph is Eulerian if and only if its edges can be partitioned into disjoint cycles. That means the whole graph can be broken down into separate loops that don't share edges. Second, a graph is semi-Eulerian if it has exactly 2 vertices of odd degree. These 2 vertices become the start and end points of the Eulerian trail. To actually find an Eulerian trail, we use Fleury's algorithm. It has 2 simple rules. Erase edges as you traverse them, so you don't reuse edges. Avoid using a bridge and edge that would disconnect the graph unless you have no other choice. This ensures you don't get stuck before covering all edges. Let's now return to the question that started the study of Eulerian graphs. Can you cross each of the 7 Königsberg bridges exactly once? Using what we learned about Eulerian and semi-Eulerian graphs, we can analyze the situation. When Euler represented each land area as a vertex and each bridge as an edge, we heard that all 4 vertices in the graph had odd degree. From our lesson, a graph is Eulerian only if all vertices have even degree. Is semi-Eulerian only if exactly 2 vertices have odd degree. But the Königsberg graph has 4 odd degree vertices which violates both conditions. This means Eulerian trail and no Eulerian circuit. So the answer is no, it is impossible to cross all 7 bridges exactly once. Euler's analysis of this very question became the foundation of the theory of Eulerian graphs. In summary, Eulerian graphs allow us to analyze and design routes where every connection must be used exactly once. From classical puzzles like Königsberg to modern applications such as postal routes and network traversal, this concept remains highly important. Thank you, and I hope this helped you appreciate the beauty and logic behind Eulerian graphs.